All right, let's go and review some things we've been looking at lately. We're talking about parametric equations. What are parametric equations? Quentin?
Equations that use a third value to graph the shape.
Okay, it uses a third variable, and we call that third variable the parameter, hence the term parametric equations. What's the purpose of the parameter, Jamie? To limit the graph, so that rather than graphing, for instance, an infinite straight line, you're graphing a line segment. Instead of graphing an infinite parabola, you're graphing just a piece of the parabola. For instance, let's do some classwork very quickly. You'll get some graph paper out. X equals k plus 3 and y equals k squared. Here, of course, the parameter class is k. And we're going to limit k between negative 3 and 3. And by putting a limitation on k, it thereby limits x and y. At your seats, go ahead and graph these parametric equations. Good, looks like all of you set up a KXY table. Check your work, see how we did. Jamie's looks good, and Quentin's also looks good. All right, questions on this? But let's suppose I didn't put a limitation on the parameter. Well, then at that point, what would happen to my parabola?
Go to infinity.
Yeah, go to infinity, at which point we might as well just know the equation of that. So the last thing we looked at in our last lesson, what we did for our homework, was we eliminated the parameter. How did we do that? I know we're going to look at the homework in a minute, but let's refresh my memory. How do we eliminate the parameter, either of you?
Solve for it.
Solve for, in one of the equations, preferably the easiest equation, which would be the top equation. Rewrite this as
k equals 3 minus x, or
x minus 3, and then we can take x minus 3, plug it in here for k to get, Jamie,
x squared negative 6x plus 9.
There we go. And here we see the parabola, right? We see one squared variable, one not, and there's our equation there for the limitless parabola. That's what we worked on the homework. Let's go and take a look at page 201, numbers 2, 9, and 10. You are eliminating the parameter from these equations. And again, that's all you would do if, and of course then we could analyze it as well if we wanted to, right? If there's no parameter, we could analyze intercept, symmetry, domain and range, all that stuff if we so chose. Number 2 from the homework, they gave us x is equal to t plus 2 and y is equal to t squared. This is very similar, actually, to what we just did, Jamie.
Move the 2 over to get t equals negative, or x negative 2, and then substitute that in and square it, and it's x squared minus 4x plus 4.
There we go. Is this what you got as well, Quentin, for number 2? All right, number 9. Now, they technically did give you a limit on the parameter, but I said we're going to ignore their limit, and this is a little boring. This is basically just like the last one. So, Quentin?
So t equals x and squared, so x squared minus 2x plus equals 1.
There we go, and there's our equation for number 9. Good to go on number 9. Hey, number 10, finally, a little bit of a change of pace. T squared plus 1 for the x, and then y equals to 2t. And what did we do for this one, Jamie?
I divide both sides by 2 on the bottom equation.
Okay.
And so it left me with t equals y over 2. And I substitute that in for the other equation. And so it's x equals y squared over 4 plus 1.
But since we really hate fractions, Quentin, what might I do to fix it up a little?
Multiply everything by 4, so 4x equals y squared plus 1.
And this is the better looking version, just because I really hate fractions. All right, and not sure why I didn't circle that one, but there we go. There's our answers to the homework. Any questions on eliminating the parameter? All right, another thing that we worked on recently was finding points of intersection. So if you had a couple of graphs, you could locate, without even graphing them, where they would intersect. How do I find points of intersection, class? Ooh. Points of intersection. System of equations. We're going to use a system of equations. So for instance, if I gave you this equation, x squared plus 8y is equal to 16, and I gave you this equation, 3x plus 4y is equal to 12. Well, what's the top equation's shape?
Parabola.
Parabola, 1 squared, 1 not, lower equation.
Straight line.
Straight line. And if I want to find where they'll intersect, just solve the system. And a couple ways you could solve it. Your seats, I want you to find the points of intersection, if there are any. How many points are we expecting?
1 or 2.
I'm expecting 0, 1, or 2. I wouldn't be shocked by 0. 1 would actually be a little surprising. 2, I'm kind of more expecting 2 from a line in a parabola. How many are doing substitution? No one doing addition. Interesting. All right. Do either of you think to do this? Treat the 8y as a double 4y.
Oh, actually,
Solve for 4y and plug it in for the 4y.
I did.
You did? You actually got a letter all the way by itself, which is more conventional?
No.
It's not wrong to do that, but man, I think it's a little easier substitution here, right? Because then I can take, well, 2 times The 12 minus 3x, Jamie, pick it up from here.
That gives you 24 minus 6x.
And of course, we have the x squared at the beginning still. And then from here,
I did the same thing. I moved the 6 numbers and negative and got x squared minus 6x plus 8. Then backwards pull and got x minus 4 and x minus 2, which gave x to be 4 and 2.
all right, so that means we've got two different x values of intersection. Now, here's where it's a little more annoying is if you didn't get the y completely by itself, which you did, in your case, you already had the over 4. We have that one more step to do. If we plug in a 4 right here, what do we end up getting, Quentin?
0.
0. And if we plug in the 2 right here, we end up getting 6/4 reduces to 3/2, or we could say 1.5, and there's our other point. Now again, nothing wrong with plugging that in because the 4 and 8 would cancel anyway, but it's a little quicker way. I did want to show you that technically you could add if you multiplied the bottom by a 2, because that would give you a 6x, an 8y, and a 24. And if you change the signs, say, here, this cancels. Now this doesn't combine. I still get x squared negative 6x. Here, I get negative 8. So because there were some like terms, you could do the addition method, and obviously it's going to get you to the same point again, isn't it? But a few ways in which to approach that same problem. Questions on this? Let me give you another one. Let's take 3x squared minus y squared equals 11. What shape is that? Hyperbola, because of the minus. And let's take an x squared plus 2y squared equals 6. What shape is that? They're both squared.
So, ellipse?
Ellipse, because the plus here. And so how many places could a hyperbola and an ellipse intersect? Max of?
Max of 4.
Max of 4. All right. At your seats. All right. How did you choose to solve this one, Jamie? Addition or substitution?
Addition.
Addition? How did you solve it, Quentin?
Addition.
Also addition, okay? We could solve substitution, nothing wrong with addition, though if I use the addition method, we're going to want to multiply the bottom by 3, or I like top by 2 because they already have different signs. If you multiply bottom by 3, then also have to pick an equation to change the signs. I'd rather have the 6x squared minus 2y squared equals 22 and just allow those to drop out. Which would give me,
7x squared equals 28.
which gives me x squared equals, well, 4, so x equals positive negative 2. That's if we solved it that approach. So that gives us a 2 and negative 2 for my x values. Then I'm going to take the 2 and or negative 2, plug it back into either the top or bottom equation. Bottom has no negatives. I like that. So you square a 2, first of all, it gives you a 4. You move the 4 over as a
negative
to get
2.
So we're at a 2y squared equals 2. Divide away the 2 to get y squared equals 1 and y equals
1.
All right, so when we plug in a 2, we get a 1 and we get a negative 1. Well, you know this. If we plug in a negative 2, what's going to happen? Same thing. So I'm going to get a 1 and a negative 1. And there's the 4 points of intersection I said I could get on this problem. Now, if you multiply the 3 through the bottom, change the signs of one of them, you'd end up getting the positive negative 1 first. and you're getting positive, negative 2s later, but same 4 points of intersection. Questions on that? Any questions on systems of equations or parametric equations? We've got a quiz coming up here. Any questions on either of those concepts? All right, clear your desk except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, calculator, everything else away. And this is quiz 31. Quiz 31. You're going to take it on my paper though, so you don't need to write anything on your paper. That paper is simply for a cover sheet. Or if you need to do some work on there, though there should be enough room on the quiz copy to do all of your work. So at the top of your quiz paper, if you write your first and last name, along with today's date, 2/14/22, or you can just say Happy Valentine's Day, or you say, I love my favorite math teacher ever, or whatever you choose to put at the top of your paper where it says the date. Pretty straightforward. You have 3 systems of equations to solve. Solve for the points of intersection of those systems. And then number 4, there is a pair of equations for you to solve, and a bonus at the bottom. All right, there is not going to be any homework this evening. Our next lesson is going to be in preparation, just a review lesson. So you start reviewing for your test coming up in lesson 115. But there will be no homework for this. Just make sure you have me go over your quiz before you try to take that test in lesson 115. You may begin.